Welcome. So we know how to construct the dual problem from the given original linear programming problem from the previous slides. Then what is the good thing about knowing the dual problem? One important fact about the dual problem is that if the original linear programming problem has a solution, then the optimal value of Z obtained from the original linear programming problem will be the same as the optimal value of Z obtained from the dual problem. More specifically, the minimum value of the objective function in the dual problem is the same as the maximum value of the objective function in the original problem. Besides, there are also other common features we can observe from both of the linear programming problems. Namely, the value of y1, y2 up to ym, for which this minimum is obtained in the dual problem, will be the coefficients in row 0 corresponding to the slack variables in the original problem. The value of yi is the coefficient for si. Please be careful that when we are referring to this second remark, we are referring to the coefficients of row 0 corresponding to the slack variables in the original problem when the simplex method of the original problem has reached the final tableau. We are not referring the coefficients of row 0 from the first tableau of the simplex method of the original problem, but we are referring to the final stage of the original problem. We shall illustrate these two facts by using the example on page 7. In this example, we are given the linear programming problem, which is a maximization problem with constraints inequalities involving less than or equals to symbols only. We have got the dual problem to this original linear programming problem. First, we shall solve the original problem by using the simplex method. Please refer to the following deductions by yourself. We shall come to this final tableau, which the first row no longer consists of negative coefficients for the variables. Therefore, the solution will be optimal as long as we take the value of x1 to be 20, x2 to be 30, s1, s2 to be 0, and the corresponding value for z will be 280. Therefore, z has a maximum value of 280, which is achieved when taking x1 equals to 20 and x2 equals to 30. We have already formulated the dual problem, and we have just solved the original problem by using the simplex method. Now, we would like to determine the optimal solution to the dual problem from the optimal tableau of the original problem. If we refer to this fact, the minimum value of the objective function in the dual problem is the same as the maximum value of the objective function in the original problem. So, since Z has the maximum value of 280 in the original problem, therefore, corresponding to the dual problem, with this new objective function, this Z has a minimum value of 280 in the dual problem, and these two values will be the same. On top of the first fact, please also refer to the second fact. You can observe that when we have solved the original problem, this is the final tableau we achieved. We observe that in the 0th row of the final tableau here, the coefficient of S1 is 3 over 5 and the coefficient of S2 is 8 over 5. According to the fact here, these two values will be the values of y1 and y2, referring to the dual problem when the minimum value of 280 is achieved in the dual problem. That is, when we know that the Z in this dual problem has a minimum value of 280. This is achieved when taking y1 equals to 3 over 5 and y2 equals to 8 over 5. And this 3 over 5 comes from the coefficients of the first slack variables in the 0th row in the final table of the original problem, whereas the 8 over 5 for y2 comes from the coefficients of the second slack variable in the 0th row in the last table when optimal solutions of the original linear programming problem is achieved.